What's going on, guys? I just want to show you what I've been working on as far as the motor controller goes from the Arduino side. Um, because I've worked with these Saber-Tooth controllers before, and I know they support analog input, so you can hook up like a potentiometer or joystick. Right now we're using RC or PWM input, but they also support these serial protocols. Um, and I was wanting to look and see how difficult it would be to use the packetized serial. Um, and turns out they actually do have Arduino libraries just ready to go. Um, you can download them, and once you download them and install them, you can see them in the examples. So for like Saber-Tooth, Basics, the Sweep, and this is what I integrated into the old code. And so it's about 52 lines here, but it's pretty simple. Like you just have in order to get it to work, you have Saber-Tooth include right there. You have this object. Um, and so for us, because we're using serial 2 and we want to use the original serial port for ROS, we would have to specify serial 2 there. I believe that still works. Yeah. Yeah, so that's how you do that. And then this will just starts the serial port, and then if you read this down here, it says it'll save you 2 seconds on startup delay. So I don't really think we need that because by default it should be 9600. As far as this address right here, which is what this is, because you can have a bunch of motor controllers hooked up to the same serial port, and then you can address them separately. And then it's also a packetized system where each packet has a checksum, and basically you're not going to get any kind of jitter. But you set these with diff switches. The manual for the motor controller has all that in there. Um, but in order to then drive the motor, well, they're doing it. This is independent control, so like motor 1, motor 2. You can just say like st dot drive, and it goes from negative 127 to positive 127 for full forwards and full reverse. And then you have st turn. Oops. And same stuff. Negative 127 to 127. And so this basically replaces the pulse out, where you would send a PWM signal, which would then have to be interpreted. Um, and it's so easy to do that it's worth checking out. So I basically just took this and drug it over to drug it over here to the original one. I split it apart into 3 different tabs here. So this the main one mainly just has this loop, and it switches between the modes. And then we have an update RC receiver, and then update motor control function call in the main loop. And we also have a setup RC receiver and setup motor control call. All this stuff up here, it's got to be here because this is the global area. So like if I defined it up here, it wouldn't be visible or writable to the main code. So for the motor control, I just kind of copy and paste it. The only other thing you have to keep in mind is the robot does have an arm pin. So like you'll hear it, it'll click like on and off, and I guess it physically disconnects the motor controller. But this is the initial setup, so it sets that low, sets up the pin as an output pin, initializes this is the forward and back speed, and this is the rotational speed. There's a motor stop function that will arm the motors and then set them to 0 for 1 second. And then the update motor control, all it does is it just says st.drive, st.turn, these amounts. And so that's it for the motor control tab. The RC receiver, so in order to take these PWM values right here that we read with pulse in, they typically go between 1000 and 2000. We need the byte, or the normalized byte value between negative 127 and positive 127, so that we can, because in the manual drive mode, we're just setting the motor linear velocity to the RC pitch and motor angular velocity to the RC yaw. And the way it's scaled, it should work the exact same as it was working before. And so that's what this normalized to byte value function does. It returns a signed character or a signed byte, and then it takes the raw PWM value in here, and then it just does this little expression to get the normal value in an int, because it may be higher or lower than what we need, and so we got to have it as an int so that we can check it, and then we just check the bounds of it right here, and then we return it as a signed character. And the update RC receiver is a little bit different. So we have a temporary variable, which is the new raw value. So we'll pulse in the elevator pin, which is the throttle forward and back, and we'll put it in the temporary variable here, and we'll check it to see if it's 0. Because if it's 0, that means that it timed out. So if it's not 0, then we update the RC pitch raw, and then the normalized pitch values. And then it just gets repeated for the turn and then the throttle. These debug statements, they're just macros that I defined over here. So like debug 0 is this main loop, and then you got debug 1 and 2. That's the update RC receiver, update motor control. And basically you can come down through here where it says if I wanted to see what it was getting from the RC receiver like I am now, it's turned on. So it's just spitting out what it's receiving, the raw value on the left, and then the normalized value on the right. But I mean, you can turn it off just by typing 0 there. And that's pretty much it. I just kind of tried to clean it up and organize it a little bit. But I think me and Alex may try to wire this up tomorrow, because we will have to change some wires around. But it was so simple. I mean, even compared to the code that he provided, it's way simpler than that. So it's also like 10 times as robust. So we should definitely check it out to see if it'll be as easy as it looks. So I'll take it easy.